Now what happens to the probability measure? So we had a probability measure P. What happens to this? We don't consider any sort of subset. So when we consider sigma algebra, right? So what sort of subset do we consider? Actually there is a, what is the symbol? So we consider particular type of subsets which are called Borel sigma algebras. Okay. So what sort of subsets do we consider? Of course, measurable subset. And what sort of subsets? But in particular, we consider subsets that are of the form. So if you are looking at R, if our range space is R, we consider subsets that are of this sort. If it's in R, so this is a subset in R. Similar thing in RD. This is the kind of subsets that we consider specifically under random variables, and these subsets are called Borel sigma algebras. Okay. Now, so now what happens is, what happens to probability measure? So now what we have to talk about is that, so there exists a function that operates on sample space, elements of sample space, and it maps that onto some element in real numbers. Okay, which means that the subsets of the sample space also gets mapped to something under this function, and those sets are Borel sigma algebra elements. Now, since we have assigned measures on the elements of F, there should be something equivalent here as well. Correct? So what does that mean? So it's like this, right? So we have assigned probability measure on the subsets of F, and these subsets gets mapped to some element or some subset in some subset of R, right? Which means that there should be some equivalent in this new space that corresponds to the probability measure. What is it called? It is called the distribution function. Or also the probability distribution function, or also cumulative distribution function, and so on. Also called a push forward measure. That's the terminology that is used. The idea is that you have a measurable space, the triplet, and you define a function on top of it, and a new measure emerges. So it's called a push forward measure. So starting from, so let's define this. So if you take, and my notation is this throughout the course. If I write script P with a subset X here, I am saying that this is the distribution function under the probability under the random variable X. So if I evaluate this at some small x, okay, for ease of understanding, let me do it for one dimensional. Let me take D to be 1 and do it. It's easy to comprehend that way, and then we will generalize this to the D dimensions. So suppose I evaluate this distribution function, okay, Px at some x. What will this give? This is defined as the probability measure, okay, that is assigned to a set, because the probability measure is always assigned to a set. What set? In fact, it's the subset of the sigma, element of F is what the probability measure is assigned by definition. Okay. Now, if I take a small x and evaluate this distribution function at that small x, what am I saying is, I am just saying first consider a set which is of this sort. Take a subset of R, which is this, and see what is the inverse image of this set under the random variable X. What does this mean? Remember that random variable is a function from the sample space to R. Now, if you take a subset in R there should exist a reverse image, inverse image of that subset in the sample space, a subset of sample space. You consider that subset, and that subset has a probability measure, right? That is what the distribution function evaluates to. Does it make sense? Right? So this is probability of n event A, which is equal to, which is the inverse image, right, of the subset minus infinity to x under the function called random variable. What is the probability measure of that particular subset of the sample space is what this distribution function evaluates to. Or I can say, not say equal to, right, its better notation is A such that it is the inverse image of this particular subset. See, this thing, see if one of you may correct me, it's open at one end, right? It's open here, right? Yes. Yeah, thank you. Hold on. Let me repeat. Probability distribution function evaluated at a point x. See, what is this small x? What sort of element this is? This is a real number. This is a real number. So if you evaluate, door, close the door. There's some noise. Hold on. Let me think about it. It's closed at x and open at minus infinity, right? Yeah. This is open here, closed here. Thanks for that. I keep saying this, right? So this proves that I am not an AI, or rather not, because AI hallucinates too. And you know what? These systems have been trained by using an algorithm called RLHF, reinforcement learning using human feedback. They have been trained in such a way that they are, see, because humans like to get confirmation biases. You know what a confirmation bias is, right? So when we talk to people, we don't seek their opinion. We want them to acknowledge what we say. This is called confirmation bias, so because humans seek confirmation biases, and since the labels are coming from humans, if you do RL using human feedback, these systems tend to mimic confirmation biases. Do this experiment. Ask a simple question to an LLM. Okay? Tell that this is wrong and give a wrong answer. It will say, yeah, I was wrong, and it will say, this is right. So yeah, anyway, so here is what distribution. So I mean, me making mistakes and correcting them does not prove that I am not an AI. Yeah. So at the end of this course, we should find out what makes us humans. Yeah. Okay. Anyway, so the definition of a distribution function is that if you evaluate the distribution function at a real number, first we construct these sorts of sets, minus infinity to x, and see what is the inverse image of that particular set under the random variable that we have defined. So that corresponds to some subset of the sample space, and that look at what the probability measure that is assigned to that particular subset, and that's what this probability distribution function evaluates to. Does it make sense? Okay. Yeah. Questions on definition?
X was any real number, right? Now, if we have any interval here, how do we know that the image of that will correspond to some there will be some subset?
That's how we have that relates to the question that he asked, right? The way you define your random variable is such that the function has to have an inverse image given Borel sets. When you define random variables, you define it in such a way that the inverse image of Borel sets always exists. Okay. Any other question? No. we have already defined the probability measure. Is your question how is the probability measure estimated in practice? That's the entire course. The entire the central question that we take up in this course is, given elements from the range space of random variables, estimate the underlying probability measure via distribution functions. How is it assigned? We don't know, nature does it, or some labeler does it, depending upon your problem. If your problem is supervised learning, then the labeler, see the question that you are asking is, how would a doctor know whether a given image is diseased or not? See, I have worked with doctors, they would say, this, they see this, look at this, and there is some intuition, something, they can't put it in words. So we assume that the measure is assigned by nature, or the problem, or whatever, right? Our job as engineers is to estimate this measure given samples from the underlying distribution. That's what I will formulate it to be, yeah? Anything else?
Sir, how will this Boolean sigma algebra will look like in a R2 domain?
R2. That's why I told you to refresh your probability theory basics. So the question is, how does the Borel sigma algebra look in R2 or RD? Any guesses? It should have been done in Stoma, right? How would it look? How would it look? Yeah, Cartesian products. The Cartesian products. You take one dimension, the other dimension, take the Cartesian product, that's how it looks like. Yeah, see, that is why you have things called joint distributions and vector valued random variables. We will come to that in a while. See, now it's all we are talking about is that we have a sample space and the mapping is to a real number, right? So what if it maps to RD? Then this random, the range space, what if the range space of this random variable is RD, right? In fact, these ideas are very extendable, no? See, what you see in one dimension, in n dimensions or d dimensions, they are just the Cartesian products, that's it, okay? Is this clear? So now from this triplet, we got another triplet. What triplet did we get? We got R, B, and what made this transformation possible? Now tell me if this is a variable. This is not at all a variable. I just can't see that as a variable. It is a function, okay? A push forward function that would take one measure space to the other measure space, and we deal with this, in machine learning, we work with this. See, from now on, I will not talk about omega fp. I will only talk about R, B and Px. Is that okay? Because the moment we measure something or we have a sensor and have some data as vectors, we are operating in the push forward space, and we assume that there exists a random variable, okay? So now you see, you appreciate why somebody needs a random variable in the first place. So it is, a random variable is not defined randomly, right? So there's a lot of thought that has gone behind this. Does it make sense to all of you? Okay. Right. Now, okay. So one important idea that we have to know before we move forward is that the random variables with vector valued range spaces. See, seems trivial, but pretty important to know. See, we said that a random variable is a function that takes omega and maps it to R. It need not map it to R. I have already told that to you. It may map it to RD. Okay. So now in general, the random variables have Rd as their range spaces. Okay. So x is a function from omega to Rd. See, these are also often referred to as vector valued random variables. Maybe I should write that. See, it's a sort of misnomer. See, what do you mean by vector valued random variables? All I am saying is the random variable is a function and the range space of this function are vectors and they are Rd, that's it. Well, that's a better way to say it, isn't it? Okay. Now what happens is, somebody asked, what happens to the sigma algebra in this case? They are Cartesian products. So we are looking at, if it's R2, then we are looking at sets like minus infinity to x1 in one dimension, right? This is one set. It's open here, closed here, cross if it's a two-dimensional Cartesian plane that we are looking at as range space, then we are looking at these sorts of sigma algebras, right? And I hope that all of you understand this cross, right? Cartesian product, what's a Cartesian product? If you take two-dimensional space, right? So it's if this is x1 and this is x2, then what space is this? Minus infinity to x1 is everything that is below, and minus infinity to x2 is everything that is to left. So we are looking at this space, right? This space. Okay, that's what it is. And you extend this idea to d dimensions. That's a vector valued random variable. Okay. Now, what happens to the distribution function here? So now distribution function gets evaluated. Always remember this. The argument to distribution function are the elements of the range space of the random variable. Always. Correct? Let me repeat. The arguments for the distribution function, so if you want to call me that, I will say that the input to the distribution function, right, is always the elements of the range space of the random variable. If the range space of the random variable is Rd, then the argument for the random variable, the distribution function would be Rd, elements of Rd, right? So a vector valued random variable, if I have to use that word, so the input to this is some x, which is an element in, this is an element in Rd. And please bear with me when I write this x here and x here, these two are different. This is the random variable x and this is one element from Rd. Right? If you want, I can see as we move forward in the course, you will see that I will run out of alphabets and notations. Too many notations, right? Because so yeah, I will use capital X for vectors, right? And I won't change this. Just read this as bold X, okay? If I write a subscript here, read that as bold X. Okay, and this is an element of element in Rd. Okay. Now what is this? So if I say that I am evaluating the distribution function at an x which is an element in Rd, what do I mean by that? I mean, it should again remember that the distribution function always corresponds to the probability measure. Distribution function is a valid measure. The density function is not, by the way. If somebody tells you that evaluating the density function gives you probability, they are very wrong. We will see that in the next class. If you evaluate the density function, probability density function at a point, you won't get probability, because probability is a measure. And because you have defined a random variable as a function on the sample space, distribution function is also a valid measure, because it's actually evaluating the probability measure, not the density function. This is only for you students sitting in the class, because I have not formally defined what a density function is, which I will do eventually. But anyway, probability distribution function is a valid probability measure. Okay. So now if I evaluate the distribution function at some x, what am I talking about? I am talking about the probability of an event which happens to be the inverse image, okay, of the Cartesian product that is taken under the random variable in the event space. That is the probability, that is the event whose probability I am talking about. Please note that this event, right, is a subset in the subset of the sample space, and it can be a singleton set, by the way. And in the X-ray example that we took, it can be the probability of that X-ray being diseased. It can be that. You get it? Okay. So now what is this? This is actually the probability. See, whenever I write probability, I mean the measure. It's nothing to do with the colloquial probability. I am talking about the underlying measure. Yeah, it's the probability of the inverse image of that particular event. See, I can't write that entire set. So it is inverse image of Cartesian product. Let me write it there. Product under X. Yeah. See, I will skip, this is not a course on probability theory. This is just to whet your appetite on probability theory. Please, you should do an entire, that was a prerequisite for this course. So do a formal course on probability theory. So now I will rush through things. Now what I will do, I think I will stop the class here, and in the next class, I will maybe half of the next class I will sort of rush through the other ideas, but I want you people to kindly go back and refresh your probability theory basics, specifically these things. So we talk of something called joint distributions between pairs of random variables. So there need not be one random variable, right? There can be multiple random variables. If we have multiple random variables, we are talking about multiple sample spaces, because every random variable is a function that is defined on random on a sample space. Now imagine that you are tossing a coin and you are rolling a die, and there are two random variables, and we can talk about interaction between them. And there are two random variables, and we are talking about the interaction between those two. And what do you mean by interaction? That's too vague, right? So in set theory, if you have two sets, you can talk of, you can take elements of those two sets, and you can talk of different kinds of set operations on two of them, right? Exact same thing happens when you talk of random variables. That's it. Because random variable is a push forward measure, everything that happens on sets can happen on the random variables. Now in the X-ray example that we took, let's say that somebody getting a disease or not getting a disease and being imaged is one sample space, okay, and the process of imaging is one sample space, and the mechanism of obtaining or not obtaining a disease is another sample space. You can view the process of having an image or not having an image as a coin toss, and it has nothing to do with the fact that this person went through an X-ray or not. Do you see that? These two things may be correlated, but they can be seen as two different random experiments, outcome of two different random experiments. Do you see what I am saying? This is very, very important, right? Somebody getting an image or an X-ray image is one outcome of one random experiment. Somebody getting a disease or not a disease, not getting a disease is the outcome of another random experiment, and we can talk of interactions between them, and that's the labeling process. Do you get what I'm saying? In fact, somebody developing a disease and getting a disease, or rather somebody getting a disease and getting an X-ray can be seen as the outcome of one single random experiment. See, as I told you, this notion of random experiment is completely up to the user. So that way, in my mind, a vector valued random variable can be seen as a union of multiple scalar valued random variables that are correlated. Or it depends. Now you see the point, right? See, when we talk of a Gaussian distribution of a vector or a vector valued Gaussian distribution that we talk of, we talk of this correlation matrix, right? So what is a vector valued Gaussian random variable? It's actually the union of multiple scalar valued random variables. You can either see that as one random variable, okay, which has one underlying sample space and the range space is a d-dimensional vector, or you can see that as d scalar valued random variables interacting with each other. You see the point? And this is why you have distributions over vector valued random variables. And I will actually make this notion a little more concrete next time, because in this entire course we will be talking about distributions over vector valued random variables. Okay. Now in this world view, there is a nice unification between even the discriminative and generative models. To me, both of them look the same. So labeling is simply one dimension of the vector valued random variable that we are looking at. See, that is where we can define conditional distributions, right? As since we can define sets, okay, which is the intersections and unions of the sets, we can define conditional distributions that way. Okay. So anyway, so I think this is a good point to stop. Please go back to your probability theory basics. Specifically look at what does it mean to say that there are multiple random variables. What does it mean to say that there is conditional distribution and conditioning of random variables in terms of, see, try to relate everything that you see now to the sample space and the underlying sets. So that actually makes notion very, very clear. Conditional distribution has to do something with the sample space, right? So ask yourself, what is the event that I am considering when I am looking at conditional distributions? Okay, so please do that, and look at what distributions are and what are the discrete random variables and continuous random variables and so on. I will not do all of that because, as I said, this is not a course on probability theory, but half of next class I will give you a quick run through of some of the key ideas, and then we will connect, or rather formulate, the problem of machine learning in terms of distribution learning. Okay. This concludes the topics that I wanted to cover in this particular class, where we looked at the definitions of sample spaces, probability measures, distribution functions and so on. In the upcoming class, we will be looking at multiple random variables and the ideas of conditional distributions and so on, and connecting them with the problem of function approximation and define the core problem of machine learning. Thank you for attending this class.